Hi everyone, in this video I'm going to give you an example for diffusivity inversion. So we have a forward model given by a diffusion equation of this type where our diffusivity coefficient m is what we are inverting for, and typically for a diffusion equation you have this time dependence, but we're going to assume we're in an equilibrium state, so this term vanishes. What I mean by that is typically, if you view this as a time-dependent process, say we have starting high concentration here in the center of the domain, and sort of the random directions of these velocities lead it to approach this uniform density here on the edge, or more uniform density. And once we hit that equilibrium state, this derivative is 0, and so we get this equation. So we want to see what that equilibrium state looks like. Furthermore, we impose a 0 Dirichlet boundary condition on the edge of the domain. So it's not allowed to transport outside of this area. So as standard procedure in inverse problems, we want to find the weak form of this PDE. So all we do is we multiply by a test function v, and then we integrate. Hold the derivatives off, we integrate by parts. Pull the derivative off of this term, which we need twice differentiability on this term. So to make it symmetric, we make this differentiability criterion weaker on u. And so this is the boundary of mv u dot n plus the integral of omega m del u dot del v equals the integral of f dx. And then if we set v identically 0 on the boundary of omega, just like we set u to be 0, we impose that boundary condition, then that term vanishes to 0. And so our weak form becomes find u in h01 of omega. And just as a review, this is the set of all functions g in L2 of omega, such that the gradient of g is in L2 of omega, and g is identically 0 on the boundary omega. Such that for all v in h01 of omega, the integral of m del u dot del v equals f dx. Okay, so now we have the weak form of our PDE, and we want to impose that constraint on our system. So ultimately what we want to do is we want to minimize, this is our misfit term, this is our regularization term. So in this context, in the continuous form, this is the continuous form of Tikhonov regularization. And this penalizes large gradient of the diffusivity field M. And so in other words, this smooths our operator. And then we have to constrain via the Lagrange multiplier P our weak form of the PDE. So we subtract this to the other side, we need it to be equal to 0, so this is V gets replaced with our Lagrange multiplier P, and that is our Lagrangian. And the adjoint state method just says, first, step 1, find u in h01 of omega such that for all p hat in h01 of omega, partial Lagrangian, partial p hat is 0. And then this is just m del u dot del p hat minus fp hat dx. And notice here that it's exactly the same as our weak form, because v is a dummy variable that we vary over. So it's literally just replace v with p hat and then vary over all of them. So it's literally the same problem that we just derived. As it should, that's basically how it should always work out, because that we're constraining that to be true. That is what we say the physics is. Second, we solve for the Lagrange multiplier. We solve this variational problem. We take a partial derivative with respect to u acting in the u hat direction. We set this equal to 0. If we go back up to our Lagrangian, we have a u term here on this green in the misfit. We have a u term here in the blue. This regularization term does not depend on u. So taking a derivative with respect to the first term, this is u minus d times u hat plus m del u hat dot del p dx. That's our adjoint equation. And then finally, we evaluate the gradient. Partial in the m hat direction. So let's go back up here. So the misfit does not depend on m. We have this regularization term, and we have m on this term. So we should just have two terms here. So for the regularization term, this will come out to be, and then this one would just be m hat del u dot del p dx. And now these are known. M is our current. M is also known at the very beginning because this is our current guess. So we always have to guess an initial model parameter, and then we iterate on it through gradient descent. That's always known. And then notice that we are not setting anything equal to 0. Because we're at this point, we're evaluating the gradient. So this gives us a workflow that now we can do gradient descent here. That's the main takeaway from this. So in the next video, we'll extend this to say, okay, well, that's nice, but why did you tell me about Newton methods and Newton-Krylov earlier? Well, in the next video, I'll show you how to extend this to computing the Hessian action in continuous form. And then after that, we'll take our continuous form and discretize it and then actually solve the inverse problem. And I'll show you guys some computational examples with it. Thank you guys for watching, and I hope to see you in the next video.